Hello. Hello, everybody. Welcome to the jungle. Today, we're going to be helping you map the zero-knowledge jungle. My name is Anna. I'm the co-host of the aptly named The Zero Knowledge podcast.
And I'm Howard. I'm a partner at Decrypt that invests in privacy tech and also a researcher at UC Berkeley.
So before we kick off, I want to get the clicker.
Oh, yeah.
Do I have that?
Yep.
Cool. This doesn't work? All right. Then we'll just go this way. So before we start, very quick question. Who here knows what a zero-knowledge proof is? Put up your hand. A lot of you. Who here knows what a ZK snark is? Also a lot of you. Who here has worked with a ZK snark? Okay. So there's a couple people who didn't put up their hands, so we will do a very quick, brief introduction to what a zero-knowledge proof is.
All right. So a zero-knowledge proof is a privacy-preserving cryptographic proof of computational integrity. And this is a lot of jargon to try to say something rather simple. And on a high level, the idea is, one, I know a secret. I can't tell you the secret, but I can prove to you that I know the secret. And so a canonical example is demonstrating this using Where's Waldo. And so take a look at this map. Can anyone find where Waldo is?
We're giving you like 3 seconds. Anyone?
I see a few.
One person found it.
So I know where Waldo is, and I would like to convince you where Waldo is. And so, one way that I could do this in zero knowledge is, say I go into an empty room, there's a table, and I put this map on the table. From there, I take a giant piece of paper, and I overlay, and I cut a hole exactly where Waldo is. From there, I want to center this on the table so that it is really not obvious on the map relatively where Waldo is. I then have you come into the room, and you take a look at this, and you'll believe that I indeed know where Waldo is without revealing to you where Waldo is on this map. And this is a simple demonstration of a non-interactive zero-knowledge proof.
So zero-knowledge proofs originated in academia in the late 80s, and for a long time remained in the academic space. There was a few proof of concepts out in the world, but really it was, you wouldn't have seen it day to day. With the advent of blockchain, though, it became clear that zero-knowledge proofs could actually be used, and there was an explosion of research and paradigms and protocols created using zero-knowledge. You might recognize a few of these: Starks, Sonics,
don't forget Grot16 and GM17.
Oh yes, very important. And Dizek, which you put together.
Thank you.
All right. So the way that we've thought about this talk was we wanted to map out kind of how it's basically give you a way of thinking about zero-knowledge applications. How can we break that down? And there's basically 3 main areas: zero-knowledge proofs for privacy, zero-knowledge proofs for scalability, and kind of an emerging space, which is zero-knowledge proofs for interoperability, which seems appropriate here at the Web3 Summit. We're going to start off with the most well-known case. That's privacy. So why would you need privacy on the blockchain? As it works right now, say you're on Bitcoin, if I have some tokens and I want to send them to Howard, during that transaction, you can see that the transaction has happened, but all of you can also see that this transaction has happened. And that, for a lot of use cases, is kind of fine. It's fine if you know that. But what if I was a business? If I was a business, I would definitely want some of this to be hidden. The Zero Cash protocol, which was created in 2014, what it does is it uses ZK snarks to attest the validity of payment details while keeping them private. The most famous example of this is the Zcash protocol. Zcash is a privacy-preserving cryptocurrency. Many of you, I imagine, have heard of it. Maybe you own some. Now, Zcash is broken down into 2 things: transparent accounts and shielded accounts. If you've bought Zcash on an exchange, you've probably been using transparent Zcash. But there's also shielded Zcash and private Zcash. And what that looks like is the following. So say I have some tokens that I want to send to Howard. If I make that transaction, Howard and I will know that that transaction has happened, but none of you will. You will not be able to see my account balance, my transaction history, or my transaction future, what I do after the fact. At the same time, we need to prove that that has actually happened. And the way that we do that is to use ZK snarks to create the proof of validity, meaning it proves that if I say I sent 3 tokens, my token balance has gone down by 3, and Howard's has gone up by 3, and this is proven.
And so that is one way to effectively add privacy for payments. It's to build a dedicated blockchain where privacy is at the core. But what about for existing blockchains that have launched, such as Ethereum? How can we address the problems with transparency and privacy here? So let's observe that Ethereum transactions are transparent. And what that means is that all payments and application activity here are public. By being publicly auditable and publicly verifiable, this is really one of its strengths, but it is also one of its principal weaknesses. And namely, it's that it bears several implications. For one, the coin history is easily traceable, and this hurts the fungibility of the coin itself. 2, it allows anyone, good or bad, to monitor your addresses. And 3, it enables third parties, such as advertisers or even governments, to aggregate and analyze your spending balances and spending behavior. And the community has voiced its concerns for privacy and privacy solutions on Ethereum. Namely, sprinkling privacy on a transparent chain is not easy, and we need to find better ways to bake the sprinkles into that cake. So while no solution is perfect, given what we know today, how could we make ETH more private? And one example is a proof of concept decentralized mixer called Miximus. And Miximus is a smart contract-based approach to mixing ETH. And let me walk you through the high-level idea. So in this example, to deposit, a user would unlock their Ethereum wallet and deposit, say, 1 ETH into this Miximus smart contract. From there, the user is effectively depositing and adding a deposit to a Merkle tree, and this Merkle tree has an input to a corresponding commitment that only the user knows. To withdraw, a user will generate a zero-knowledge proof that attests to his or her knowledge of a unique commitment in the tree. And the user will then submit this proof to the smart contract, which will verify the proof and also mark the commitment as spent. The contract will then pay out the ETH to the user's wallet privately. And Zcash was an example where privacy was at the core, and in this case, we are baking in privacy into a transparent chain. And so in this case, if the user that generates a transaction for the zero-knowledge proof does not use the gas appropriately, it could lead to them leaking their identity. Now, the next area that we want to cover is zero-knowledge proofs in the context of scalability. And so scalability has been a huge topic, and there are many ways to think about scalability. One of the ways that we discuss it is primarily around blockchain storage requirements. We know that this is something that's been growing at unprecedented rates. And if we take a look at the Bitcoin blockchain size over time, we can see that it is now at 235 gigabytes. And if we looked at the Ethereum blockchain size over time, we can see that it is now at 2.9 terabytes.
Yikes.
It's pretty large. And the takeaway here is that this is neither economically nor environmentally sustainable. However, this is very important of a problem because full nodes are the backbone of decentralized networks. And so a question might be, how could we efficiently try to compress this blockchain so that it can operate more sustainably? The idea is that we want to make it sustainable and also easy for consumers to participate. It becomes a barrier to entry if we have large storage sizes and large requirements where the average consumer device may or may not be able to even store the entire state, let alone verify it. And so, one technique that's been pursued is by a protocol called CODA. And the idea here is to compress blockchain state using recursive snarks. Recursive snarks are effectively proofs of proofs, and so you can think about generating a zero-knowledge proof, and then from there, using a circuit that will verify that proof to generate another proof. And using this as a building block, the high-level intuition here is to snarkify the state of a blockchain into zero-knowledge proofs, and then compress those proofs in a tree-like manner down to a single proof. A lot of proofs. And so, with this example, it's effectively trying to take something that's, for example, 2 terabyte plus of a blockchain, and compressing blockchain state down into something that's under 1 megabyte. And the hope is that by compressing the blockchain down to this constant size blockchain, that we can achieve sustainable scalability.
But then what about scaling transaction throughput? This is a slide that I think is shown quite often. When you look at all the blockchain, the mainstream blockchains right now, they don't really compare with the centralized systems for transaction speed. They're completely dwarfed by this. Now, there's a lot of proposals on how to scale this. One of the most popular of the last few years is Plasma. With Plasma, you create a side chain, and then you do an attestation to the main chain using game theoretic methods. But what if you could use zero-knowledge proofs to actually scale transaction throughput? And there's one project that's doing that. That's Matter Labs. And what they're using is zero-knowledge proofs as the validity proof. So what they're doing is they're batching thousands of transactions, much like a Plasma would. But instead of using this game theoretic mechanism, they're using zero-knowledge proofs to create canonical entries on the main chain. This is then immutable. Now, the difference with this example and the previous one is the sidechain doesn't need to be private here. This is not about privacy. This is purely about this attestation of proof, of truth, to make sure that those transactions have actually happened. And this is not just theoretical. So Matter Labs has actually released a testnet, and they're now doing this. So this zero-knowledge proofs for scaling is live.
And it is live on
a
Rinkeby.
testnet.
It is on Rinkeby, and you should check it out. This is a proposal for a scaling solution that is deployed. It is gas efficient, and it is possible.
Oh, it's on mainnet even. If anyone's curious, there's someone from Matter Labs right over there.
And so the third area that we would like to cover is zero-knowledge proofs in the context of interoperability. And I would say that this is an area that is relatively new. It has not been very deeply explored, and so with this, here are some earlier and some of the earliest ideas that we have around this. And
definitely a space to watch, I would say.
So taking this and looking at the context, let's take a step back and just establish that zero-knowledge proofs are blockchain agnostic. Zero-knowledge proofs are not specific to any one blockchain. It is a agnostic idea that is separate from blockchains. And what if we could use this technology itself to enable the transfer and exchange of assets for multiple blockchains? Well, so there was a paper that was published called BOLT, and BOLT stands for Blind Off-Chain Lightweight Transactions. And the idea here was to use zero-knowledge proofs to enable parties to transact anonymously in payment channels. And to demonstrate one example of this, let's take, for example, how it would work with Zcash. So we have here a Zcash blockchain, and let's say there's two parties, Alice and Bob. And let's say Alice and Bob can initialize a Bolt payment channel for some agreed channel balance, and they would escrow their funds on the Zcash blockchain. Now, if Alice and Bob were to transact with each other, Alice could pay Bob by sending a commitment along with a zero-knowledge proof for that payment. Bob, upon receiving it, would verify the proof and then revoke the previous wallet state to prevent double spending. Now, this isn't just limited to Zcash, and we established that this type of stuff is blockchain agnostic. And so, for example, you could also do this on Bitcoin. And again, let's say Alice and Bob want to initialize a Bolt payment channel. They would start by escrowing funds via the Lightning protocol and then initialize a connector to Bolt. Now, with a payment channel for Bitcoin and a payment channel for Zcash, this starts to open a lot of doors. Namely, we have a generalized state channel construction here that allows for different types of applications to exist. And so, one possibility is that Alice and Bob could actually trade a Zcash BTC trading pair on a private DEX in Bolt. However, because this is generalized, you could use this to execute arbitrary computations, and it would be arbitrary computations about logic for Zcash and Bitcoin, and this is not restricted to just trading.
So, we hope you've liked this journey through the zero-knowledge jungle. As we mentioned, there's many applications that are now emerging in the wild. Here's just a few of them. If you're interested in zero-knowledge stuff, if you want to learn more, there's this thing called zkp.science. There's lots of resources out there.
I would also want to plug that Anna also runs the Zero Knowledge podcast, and she's done an amazing job interviewing founders, developers, researchers for many projects, including some listed here, getting them to talk about how they're using Zero Knowledge proofs in their applications.
And if you are around tomorrow, in the hacker node, kind of across the space, across the way from the main stage, from 12 to 6, we're going to be hosting a number of zero-knowledge workshops at the security privacy node. We're actually going to have a workshop on privacy, a workshop on interoperability, and a workshop on scaling. So we're covering all 3 of those. I'm going to be around. Howard, I hope you're going to be around. I hope my co-host, Frederick, will be around. So yeah, if you're curious, please come meet us there, and we'd love to point you in the right direction. So thank you a lot.
Thank you.